Hello, welcome to my CHE 302 Coursework 1 project. My chosen molecule is Myrocin G. Before we get into the synthesis and reaction mechanisms, I'd just like to point out some important resources I used to help me in my mechanisms and synthesis of Myrocin G, and they're listed right here. So just a bit about Myrocin G. It's a fungal metabolite, and you can see the structure of it on the right over here. It is isolated from a cellulose decomposing fungus, and the molecule itself is capable of suppressing cell growth. And this is really important because it can then be used to make antibiotic tablets for treating bacterial infections, and it does this by stopping further growth of the causative microorganism. So this is the complete synthesis of Myrocin G, and for the interest of the project, I will be using the Myrocin synthesis, as I feel this has the most chemical relevancy towards the things we learned in our past few weeks in CHE 302, and it's a wonderful synthesis, but I will only be using a select few reactions which I feel have the most relevance to our module. And along the next few slides, I will be talking you through the mechanisms. Right, so this is my first chosen reaction. It is the silation of an enone, which you can see on the left, over to a inoxysilane on the right. This is done with the help of LiHMDS and chlorotrimethyl-silane. It is a two-step process, with the first being a site-selective deprotonation. As you can see, the LiHMDS attacks the hydrogen, which causes a shift in electrons from this CH bond over to this CC bond, which will eventually create the C double bond, which you can see. However, we know carbon can only form a maximum of 4 bonds, so it needs to break this C double bond O, which results in a shift of electrons onto the oxygen, which results in it being negatively charged. We know the oxygen doesn't like this, so it attacks the TMsCl, specifically the silicon, and it results in the chlorine leaving. This leaves because it is a more favorable leaving group, and that's because it is more stable. This is my second chosen reaction from the synthesis, and it is a two-stage reaction, with the first being the iodination and then the second being the cyclopropionation. This is the reaction for the first stage, and on the following stage I will talk to you about the cyclopropionation. There is a stereoselectivity on the attack of the iodine, so because this ester group is pointing up towards us, the iodine chooses to attack from the back, which is less bulky, and it does this to minimize steric hindrance. Along with this, it also attacks it bonds to the closest carbon on the carbonyl group. So this is the second stage of that reaction, where we will be incorporating the Curie-Kowarski reaction in order to carry out the cyclopropionation of the molecule on the left, and in order to form the molecule on the right over here. We will be using a base. In our case, it is sodium hydride, and this molecule here, which is trimethyl sulfoxonium iodide. Now, before the reaction even starts, we need to create a sulfur ylide, which will act as our nucleophile. This can be done by deprotonating one of the hydrogens on this methyl group right here, with the use of a base, a strong base. Once we've created our nucleophile, we can start the reaction. Now, a little detail about the actual molecule itself. It is open to attack from here and here, because this is where, because these parts are electrophilic, so they're open to nucleophilic attack. Let me just get rid of those. There we go. Right, so the first stage of the mechanism is this negatively charged carbon attacking this carbonyl group here, and straight away we can see that it will form a 1,4 reaction. And why does this decide to attack here rather than the carbonyl group? Well, this is because our nucleophile, in our case dimethyl oxonium methylide, is a soft nucleophile which doesn't attack this carbonyl group. So this attack of this carbonyl group results in a shift of electrons, which then results in this C double bond O bond breaking, and which results in the oxygen being negatively charged. Once again, the oxygen does not like that, so it wants to reform that double bond, which results in it forming and then a electron change from this bond, this carbon double bond, all the way up to this bond here. This results in the dimethyl sulfide leaving, which is great because that is a great leaving group, resulting in a 3-membered ring formation, which then forms our final product here. Now, there's a reason why these are wedged and pointing up towards us. It's because the attack of the sulfur ylide at the start is from a top face direction. This is because there's less steric hindrance compared to the bottom side where the iodine is present. Its stereoselectivity is observed during the first initial reversible reaction. Right, so my third chosen reaction is a lithium halogen exchange with the use of N-butyl lithium. And getting straight into the reaction, we can see that the N-butyl lithium attracts the iodine, which then shifts the electron from the carbon-iodine bond onto the carbon, which results in a carbon ion forming, which then attracts this positively charged lithium. And then that's simply it for the mechanism. However, talking more about the reaction itself, it is a reversible reaction, which means results in the equilibrium favoring the more stable side, which in our case is the lithium, with the side with the lithium attached to it. And this is mainly because lithium is much smaller in size compared to other alkali metals, and which means it has a greater polarizing power, allowing it to create a stronger covalent bond. This whole reaction is kinetically controlled, and it is influenced by the stabilities of carbon ions intermediates, which you can see on the right hand side of the slide. This is my fourth chosen reaction, and it is a desilation reaction with the use of TBAF. Getting into the mechanism, we can see that the fluoride ion attacks the silicon and creates a very strong bond due to fluoride's small size and high ionic properties. This group then removes itself and acts as a leaving group, as it is more acidic and can stabilize its negative charge better than the methyls. This, after workup, then results in the OH bond.